Hi, this is Leo. I want to share some interesting work on explainable spatial temporal graph neural networks. So let me give some background information. Traditional GNNs, it only takes in one graph and generates graph embeddings for downstream tasks. But for very complex scenarios like the traffic scenarios, relationship, the interactions between different traffic agents are evolving through time. So we need to introduce another dimension, the time dimension. Here comes in the spatial temporal graph neural networks. It takes in a series of structures and captures the dynamic, the evolving information in a series of graphs to benefit the downstream task. Another reason why I choose this topic is I'm doing the protein structure modeling, and I want to incorporate the physical information from the MD simulation. So MD simulation basically puts the protein in the environment, and the protein structures will evolve in the environment. So I can get a series of protein structures. So how the structures of protein are evolving through time can reflect some physical informations. Those are very crucial. But the recent works, they didn't provide any explainable information or useful information about what information they captured in this series of structures. So I want to search for some relevant papers, and I found this causality-inspired spatial temporal explanations for dynamic GNNs. So the motivation is quite clear. The dynamic spatial temporal graphs are so complex. There are a lot of nodes, edges, graphs, they are all evolving together. We need a mechanism to understand how they evolve together. And there are two explainable strategies employed by our original paper. The first is causal inference. The second is silencing mapping. So for the causal inference, uh, the the paper described the problem by this directed graph. So for the original graph data, you'd want to split it into the trivial factors and the causal factors. The trivial factors will be the noises that are not irrelevant, uh, that are not relevant to our task. The causal factors will be useful information, and then we can further split the causal factors into the dynamic causal factors and the static causal factors. And all those factors will be work together to contribute to the downstream task, right? So if the model learn how to split the graph into those subgraphs, it absolutely understand how the data will contribute to the downstream task, right? So it can provide some explanations. So this graph is actually a combination of silencing mapping and causal inference. So here is how the model works. Remember our first task, we want to split the graph into the trivial factors and the causal factors. A very straightforward way to split this graph into two subgraphs. So firstly, the model takes in a series of graph structures and will be input into variational graph autoencoder. It will generate some causal mask, and this causal mask is to split the original graph into the causal subgraph and the trivial subgraph. So in such a case, with this mask, we can get trivial embeddings and causal embeddings, and we can use these embeddings to form positive and negative pairs into the contrastive learning. So the variational graph autoencoder is trained with contrastive laws. Finally, it can generate some useful causal subgraphs, which are reflected in the causal mask. The second task is we already get the causal factors and we want to split the causal factors into the dynamic factors and the static factors. So we are in the same way. We will split these causal factors into two different types of subgraphs. So we use the second variational graph autoencoder. It it takes in this graph and generates some dynamic mask so that the dynamic mask can split the causal subgraphs into the dynamic information and static information. The dynamic loss here is temporal pooling. This captures the dynamic information in the embeddings so that this dynamic loss can split the causal subgraphs into two different types of subgraphs. So this is a very intuitive but very useful framework. I will consider utilizing it into my current work. Thanks.